The fundamental theorem of calculus is, as the name suggests, one of the most important theories of calculus, but it's also one of the most important theorems in all of mathematics. What it says is that derivatives and integrals are inverse operations. Now, you can invert the derivative by integrating, or you can invert the integral by taking the derivative. So it comes in two parts. This is part one, where I take a function, take its derivative, and then integrate it, and basically get back the original function. So what does the theorem say? It says that if you have some function f, and it has a continuous derivative on some interval from a to b, then if you take the derivative of that function, it's a new function, and we've assumed that it's continuous, so we could write down a Riemann sum for it, i.e. a definite integral. And in so doing, we recover the values of the function at its endpoints. Now, notationally, it's convenient when you're doing calculations to have a shorthand for the right-hand side of this expression, right here, wherein I've written the independent variable x, and I've written both endpoints on the top and bottom of a bar. So frequently when we're doing calculations, we use that notation. Okay, well, why does this theorem work? What does it mean? Well, let's think back to how we run the derivative and how we run the integral. So how does the derivative work? Well, the derivative says I'm going to take a function and I'm going to ask for its slope. So let's take a look at my function. It's an arbitrary function, although of course mathematicians always seem to draw pretty much the same function. That's okay. So what am I doing here? Well, let's say I'm right here at this point, and I take the derivative. What's the derivative? Let's say that point that I'm taking the derivative, it has a slope. The derivative tells me the slope. And so in essence what it does is it says, well, if I were to go 1 unit, so this is 1 unit, then I should roughly go up by this amount. So this slope is f prime of x. And if I were to go from, let's say this starting point here is a, and this ending point here is b, and I were to add up the little slopes. So then say I'm going to go another slope, and another slope, and another slope, and another slope. What the derivative is essentially telling me, if I take steps by 1 each time, it's telling me roughly the change. The change from one step to the next. So from here to here, and then it's kind of hard to draw because it's small, from there to there, and then from this point down to this point, and then pretty much level, and then up, and then up a little bit more to get to here, and up a little bit more to here, up a little bit more to here, and up a little bit more, and finally up a little bit more. So really what I'm doing here is I'm imagining taking little steps, and as I add up all those little steps, I'll get back to my starting point here. So it'll tell me how far I've traveled in total to get from here to here. This is f of a, and this is f of b. So this distance here is f of b minus f of a. So if you want to think about it, you could say something like f of b minus f of a is equal to, well, f of b minus f of b minus 1 plus f of b, b minus 1 minus f of a. Of course, you'll notice the f of b minus 1's cancel out. I've got a minus 1 and a plus 1. Okay, well, I could keep going. I could say, put a b minus 2 here, plus f of b minus 2, minus f of b minus 3, plus f of b minus 3, etc. Eventually, I'll get to something that's like f of b minus n minus f of a. All of these guys kind of collapse like a zipper. All of these terms here, they're all equal to 0. In essence, what I've done is I've just kept track of each one of these little pieces, how much I go at each step. Now, why did I do this? Well, if you look at it, each one of these has changed in the x coordinate, what I'm putting into the f, by one step each time. So if I take one of these guys and take a look at it, this is really like f of b minus 1 minus f of b minus 2 over 1. That's approximately 1 times f prime at b minus 2, or at b minus 1, roughly speaking. Of course, if you remember your Calc 1, which maybe you do, there's a mean value theorem that says that it's actually exactly equal at some point in here, but that's not terribly important for our purposes. Now, I did it all by steps of 1. Of course, I could do steps that are smaller. All right, so I could say f of b minus f of a is equal to f of b minus f of b minus a half. Or even, let's be a little bit more aggressive here, and say b minus h. Okay, fair enough. Same idea. And eventually, I'll come down to something like, at the very bottom, I'll get f of something minus f of a. What something is that? Well, it's going to be one step more than h. Perhaps now you should see where I'm going with this. Each one of these guys here really looks like it wants to be a derivative. And indeed it is. Each one of these guys, each one of these little steps is just a derivative. Oh, okay, so what do I mean by that? Well, let's sort of zoom in on what is this quantity. What is this quantity? Well, it's not quite now the derivative, because there's like a 1 over h missing. In fact, f of a plus h minus f of a, normally you say this is like over h equals the derivative at a, right? So if I get rid of this and multiply the whole thing by h, then we're in business. So what this is really telling me is that this expression is h times f prime of b plus h f prime of b minus h plus h times f prime b minus 2h plus lots more terms f of. And if you look at this for a moment, you realize that this thing actually, I could write it out very nicely in a sum format. This is, in fact, h times f prime of b minus h times, well, how many? Times n. And this is n equals 1 to capital N. Wait. Well, they're not exactly equal, are they? They're approximately equal. But this thing looks like a sum for an area. And in fact, if I take the limit as n goes to infinity, capital N that is, of this expression, well, what is that? That's a Riemann sum. And in fact, this is the integral from a to b of f prime of x dx. Oh. And in fact, the fundamental theorem of calculus is that this is the same thing as what we started with, the f of b minus f of a. So in essence, what we've done is we've carved apart our function, chopped it up into pieces with the derivative, found out little steps, and then added them up, of course infinitely many, to get back the original function. So the fundamental theorem of calculus says that if you have taken apart your log by differentiating it into little pieces, and each one of these pieces fits together nicely, and we can take some glue and glue them together, in which case we'll end up with, well, ideally, the original log, the log we started with. And you can see, yeah, that kind of works. In essence, what we've done is we've taken the log, we break it up. That's what the derivative does. It tells you how much extra little length you've added each time. And then you glue it back together, you'll get back the original log. That's what the fundamental theorem of calculus says. It seems like a simple idea, and it really is just a simple idea.